We're so happy to have Susan Mullally here. She received her PhD from the University of North Carolina, Department of Physics. She had a family that was happy to introduce her to some observational astronomy as she was growing up. She has taught university-level classes on observational astronomy with her students. She currently pursues scientific inquiries on planets and variable stars using both the Kepler Space Telescope and the Kepler-2 photometric data. Her research also uses Kepler data to observe and characterize the parameters of other binary or double star systems. Tonight's talk, When Binary Stars Get Funky. Using the continuous high-precision photometry available from the Kepler spacecraft, the Kepler team discovered a type of eccentric, binary, or double star that they're naming heartbeat stars. In these systems, the two stars come close enough to each other to cause large periodic changes in the tidal deformation and mutual irradiation of these stars. Additionally, these tidal forces are known to cause the stars in some of these systems to ring, which will be so interesting to hear about. She will present an overview of these systems and discuss how they are allowing us to explore the physics of stellar tidal dissipation. Join me in welcoming Susan Mullally and her tale of funky stars. Thank you.
Hi, everybody. Thank you for that wonderful introduction, Linda. Hi, I'm Susan. Oh yeah, I didn't push the button. Now I have to figure out how to get to the button. I probably have to get out of here, huh? Sorry, one moment. You want to see my kid on a boat? Oh, those are my kids. That's an old picture. That one's mine. That's my little daughter, and that's my son. But they're much bigger than that now. Where's the red button on this? How do I find it again?
It should be on the USB drive.
So I have to get back to the USB drive. Ah, there it is. It's on a different desktop. Okay. Sorry, you weren't here to look at pictures of my children. I could spend an hour talking about that too, but you might all be asleep by the end of it. Okay. All right, excellent. All right, so yes, I work for the SETI Institute down in Mountain View, and I actually, my office though is located at NASA Ames, where I work on the Kepler mission. So I spend my day job actually looking for planets in the Kepler data, and then as my science time, where I get to do whatever I want, we started working on these binary systems that we started calling heartbeat stars. And they simply got their name because when we looked at the plot of their brightness variations versus time, they kind of just sort of had a slight reminiscence of an EKG of a heartbeat. And so somebody said, hey, let's call them heartbeat stars, and then the name sort of stuck. This work is not just mine by any means. I'm borrowing from lots of people, and here's a short list of some of the people I've worked closely with, and I just want to take that moment to acknowledge them. So I have very few beautiful pictures, so I wanted to start with some eye candy because I know you all are amateur astronomers. So let's take a moment and take a step back. If you think about, you go out in a beautiful night sky, you can look up at the Milky Way you see here, and you'd see these beautiful pinpoints of light up there. And when you do that, you think, oh, there's a star, and there's another star. And it's not crazy that that's the way you think about it, because you think about our own solar system. You have a sun, which is our star, and it makes up 99.85% of the mass of our solar system. You think Jupiter is a big planet, but look how small it is down here compared to the sun. Okay, so if you were going to first order talk about our solar system, you'd talk about the sun. And then you might throw in Jupiter and Saturn, and certainly you wouldn't be talking about the Earth over there in the corner, which you probably can't even see from the back. Okay, but there's one sun, there's one star. And so it's easy when you're looking up at the night sky to think, there's one star there. But the truth is you don't have to go too far away. In fact, the next star system over, Alpha Centauri, A, B, and Proxima Centauri, which this is an image of, is a multiple star system. It's either 2 or 3, depending on who you talk to. Alpha Centauri A and B are fairly hot stars. The distance between them is about the distance between the Sun and Pluto, so they're bound to each other. And if you go to the southern hemisphere, you can see this binary system. And then if you have a telescope, you can make out that there's a very cool little star called Proxima Centauri there that's circled on the screen. You can't see it nearly as well as its big, bright, hotter brothers, Alpha Centauri A and B. But this is, you don't have to go very far. You go 4.67 light years, that's not very far at all, and you find a binary system. So these things, binary systems are common. They're not every star system is it. I've heard numbers around 30% or so of star systems out there will be multiple star systems. I don't have a very hard statistic on that, though. I'm sure you could find people who could give you one. So here's what I'm going to talk about tonight. What are binary stars, and what do I mean by this, and how do we know they're there? I tend to be an astronomer who's very driven by data. I got into astronomy because I just was amazed by how much we could find out about these tiny little pinpoints of light, and how clever you have to be to figure out any of that stuff. Because at night you go out and you go, well, that's a pinpoint of light, and it sometimes changes in brightness maybe, and maybe it moves if it's a planet or something, but that's all I would see. And then I go to an astronomy class and there's all these details they can tell you. So how did we get there? How do we know that? And so that's tend to be how I approach astronomy. How do we know that? How can we measure that? So I'll talk a little bit about binary stars and what we know about them and how we observe them, or how, especially the status of things before the Kepler mission. And then when Kepler came along, and I know you guys have had talks about this before, it's a space telescope, and talk a little bit about how it changed how we could observe these stars and the amazing data it provided for us. And then I'll dive into what heartbeat stars really are. And tell you a little bit about the fun we get to have with them because of these amazing, these high tides that are risen on these eccentric binary stars. So it's going to start very general and get way more specific as we go. And then I'll try to bring you up for a breath of fresh air at the end, something like that. So how do we find binary star systems? How do we know something's in a binary system? And so there's kind of four basic ways people think about this. There's either visual binaries, astrometric binaries, spectroscopic, and eclipsing. And then at the end, you could throw in heartbeat now. So let's talk about visual binaries. Amateur astronomers know these really well. My favorite is Albireo. This was the one I'd always take my students out to observe. If you go look in the constellation of Cygnus, the swan, and you look down at its head, and you take a telescope and you point it there, you'll see this. That's actually two stars, a nice bright blue one and a nice cool red one. Now, the thing is with visual binaries is you don't know if they're actually located right next to each other in space, or if it's actually that they're just lined up well in space. One might be much farther away than the other. And so you have to be sort of clever with visual binaries. Are they moving together? Are they the same distance away? Or maybe you'll actually see them go around each other. At that point, you know they're bound, and that's what I'm talking about when I talk about a binary system. I actually mean that the two stars are gravitationally attracted to each other, that they're nearby to each other in space. So for Albireo, the orbit is not proven which way it is for Albireo. If they are bound to each other, the orbit is something like 100,000 years long or so. If you do find that they go around each other and you observe like an orbit, that's an astrometric binary. In this case, what you're doing is you're measuring the location of the star on the sky. And now all stars kind of move a little bit on the sky, especially the nearby ones. They have something we call proper motion. And just because we're moving in the galaxy and they're moving in the galaxy. And so if you go out and look at Sirius, big bright star, brightest star in the night sky, you would actually notice that it would move across the sky, and it doesn't do it in a straight line. It follows and it wobbles. And this is because, in fact, what's going around Sirius is, around the center mass actually, is Sirius B, which is a small little tiny star called a white dwarf star. It's a dead little star, it's just cooling out there. And you can barely see it at all. It's an invisible star from the naked eye. And so what you see is it wobbles a little bit. So you have these two stars going around each other. And so that's an astrometric binary. You're measuring the position of the star as it goes across the sky, and you're looking for these small changes in position. Now, most binary stars are more in this category that people know about, that people study in astronomy as spectroscopic binaries. In this case, all you see is one pinpoint of light. But, but if you took the spectrum of the star, and you took, so what I mean by the spectrum is you take all the light and you shine it through a prism or diffraction grating and you spread out all the light, you would notice these dark bands, which are depicted here. What you would notice as the two stars go around each other, the spectral lines, those dark bands, will move backwards and forwards, as you can see here. They're going, like if you just follow B, it goes there and it goes over here. And what you're actually measuring is the velocity of the star as they go around each other. So if you just followed this blue one in the middle, you see as it's moving away, it has a velocity away from you, and then it has a velocity towards you. So a positive velocity towards you would mean it's blue shifted. The line goes towards the blue. And then as it moves away from you, it's red shifted towards the red, and it repeats this dance over and over again. And so what you're really observing is your lines split and come together and split and come together. And a well-known one of these is actually, well, this is a visual binary, the horse and rider, Alcor and Mizar. But if you observed Mizar, you would find that it's a spectroscopic binary. If you actually went out and measured its spectral lines night by night, and they've known this since the early 1900s. In fact, here's the data from the oldest paper I could find on it, those little points you see there. It's a paper published by Vogel in 1901, I think. And these points are his measurements back before cameras and the computers to do the measurements for you. I can only imagine how he did these measurements. But he was able to show that you can translate these distances along the wavelengths here, along the different colors, into velocities. And so you get like a positive velocity and it goes to a negative velocity and then back to a positive velocity. And it oscillates like that over and over again. And that's a spectroscopic binary. The ones that Kepler really cares about are eclipsing binaries. And the most famous, I think, eclipsing binary is Algol. The demon star has a good name, at least. And every 2.86 days, this star just gets dimmer. It just fades out for a little bit. And then it gets brighter again. And you can imagine, before you knew what was going on, you're like, that's kind of weird. And so I think a demon star is a good name for it. And what's happening is there's two stars there, and one star passes in front of the other. And so these things are what we call light curves. The brightness versus time is what I showed you on the first screen. As the hot one, which is usually depicted by blue, is covered up by the cooler one, you get these big dips. And then when the cooler one is covered up by the hot one, you get the secondary eclipse. So primary eclipse, secondary eclipse. And it just comes from the two stars going around each other. And they happen to just be at the right inclination such that they pass in front of our field along our line of sight, so you actually block the light from one star to the other. You can imagine if you were looking at it this way instead and these were going around each other, you wouldn't see anything at all because no light would be blocked at all. So how they're positioned in space is important. Again, more data. I just get excited by data. I told you that. The great thing about eclipsing binaries is they're also spectroscopic binaries. Yay! So after you found that eclipsing binary, you can go out and get spectrum, and you can measure more about the star. The eclipses tell you something about the stellar radii. It's a direct measurement of how big a star actually is. Is it, is it 1 Earth radii? Is it the size of the sun? Is it twice the size of the sun? We can measure that from the eclipses. From the spectra, you can actually measure the stellar masses. How heavy are these two things? And this is why people like to study eclipsing binaries. Without them, we don't have a great way to benchmark what the densities of stars are and what the different varieties of stars are. And that's why binary stars are incredibly important to people who study astronomy. Okay, so along comes Kepler, phase 2 of my talk. Along comes Kepler. Kepler is a 1.4 meter telescope. It was shot off into space. Seriously, it was like thrown out into an orbit. It's not orbiting the Earth, it's orbiting the sun. And because we wanted it as far away from the bright lights of the Earth as possible. So we threw it out there. And it's in a 372-day orbit around the sun. And we pointed it for 4 years at the same patch of sky. This little patch of sky here, between Cygnus and Lyra. So we didn't quite get Vega in there. But there it is. It's about 10 degrees on each side. Now, we couldn't download all of that data because that's a lot. And so what we did is actually we took a picture of any one of our stars every 30 minutes, and we did that for 4 years. But we couldn't bring down all the data because it turns out it's expensive to store the data and then to actually transmit it down to Earth. So we actually, instead, we pulled out just these postage stamps around each star. So this is actual Kepler data you're looking at here of the raw pixels as they came down. So we have CCD cameras, and we decided we wanted this, 20 by 50 set of pixels around this star. And then every 30 minutes we downloaded those pixels, and we added up the light in each of those pixels, and we created something called a light curve, brightness versus time. Now, Kepler did this because it wanted to find planets. I can't talk about Kepler data without telling you a little bit about planets. I promise to keep it brief. But so this is what you're seeing here. It's a planet going around a star. And so every once in a while, a planet, actually I have animation of this too. If the planet goes in front of the star, you'll see that it gets a little bit dimmer, just like an eclipse. But for some reason, we call this a transit. Just the way astronomers are. We like lots of terms to confuse people. So this is the transit of a planet going across a star. A Jupiter creates about a 1% change in flux. So it's a very subtle effect that we're looking for. This is why it needed to be way off dark in space and get the best photometer possible to get the best data possible to see these things. And what Kepler's actually looking for are Earth-sized planets, which only produce a 0.01% dip. 100 parts per million is what you're looking for this little transit. I don't know if you wanted to see that again, if it made sense. So as the star planet goes across, you just get that little dip. And it did this very well. It found something, almost 5,000 planet candidates in its data set, because it was looking at 150,000 stars for 4 years with a 30-minute cadence. And it found lots and lots of planets between about the size of the Earth out to about the size of Neptune. And especially for shorter periods. It's much easier, you can imagine, to find something in a one-day period because that dip happens over and over again, versus finding something out here out in hundreds of days of periods because you have to wait an entire year before you'll see it transit again. And so we're in the process of trying to make the last catalog using the Kepler pipeline to give us the best light curves and actually come with that final Kepler planet candidate catalog. And that's one of the other projects I'm working on, so I'm happy to answer questions about that as well. But it's completely off topic with what I'm talking about tonight, so there's my little thing to the side. But Kepler, in the process of trying to create those light curves, to find planets, created a treasure trove of the measuring of the variability of stars. How Kepler observes variability. That's actually what it does. And so the thing that's great about Kepler is it was very hard to do this from the ground, especially for 4 years. And there's many reasons why this is so hard from the ground. If you wanted to take one star from the ground and measure how bright it was at a 30-minute cadence for 4 years, you'd run into many problems. The first one being telescope time. You better own your telescope. And not many people own their own telescope. Even universities usually are sharing a telescope between many different universities, or at least different people at the same university. So you end up being a very small telescope if you do have exclusive rights to that telescope. And there are some, but it's rare. So telescope time is hard to come by, especially when you start getting up to 2-meter class telescopes that you would need to do this sort of thing. The other problem is you're looking at your star, and then suddenly the sun comes up. But the truth is that's not the problem. The bright sky, that's not your problem. The real problem is that your star has set. And now you have to look through the Earth to look at your star. That's really annoying. So people solved that problem too. They started putting telescopes at different places around the world. There's global networks of telescopes. I worked for one called the Whole Earth Telescope for a while, and that was the whole point, to measure the variability of stars. And they would we said the sun never sets on the Whole Earth Telescope. That was one of our slogans out there. So there was ways around that. But even with those problems solved, you still have the clouds that get in your way and the scintillation from the atmosphere, which makes it very hard to really measure a 0.01% dip, which is what Kepler was looking for. And even then, even the best telescopes for 4 years, it's hard to get more than maybe 70% of the time or 50% of the time coverage of a star, even if you have a global network. They get 5 continuous days, they're jumping up and down, because it's really hard to do. So this is why the Kepler telescope was so amazing. And so this is some actual data from the Kepler telescope of the variety of variability it actually observed. So not only did it find planets, but it found giant stars that like to pulsate. These Cepheids and Aureliaries are a type of star that as they contract and they expand. When they contract, they get really hot and they get bright. And so that's what you're seeing here. It gets bright, and then it gets big and puffy, and it gets dim. And it does it over and over again. And so while we only observed one Cepheid star, I believe, on the Kepler mission, we did boatloads of Aureliary stars. And the cool thing about these stars is they're distance indicators. It's very hard to know how far away anything is, especially when you get to extragalactic distances. And so if you find a Cepheid out there in another galaxy, and you can measure its period, you then know how bright it is, and if you know how bright it is, you can figure out how far away it is. So that's why people studied these. Then there's non-radial pulsators, like red giants pulsate, and Gamma Doradus, and Delta Scuti stars. These actually have pulsations that move along the surface of the star. These are similar to a different type of star. I worked back in my graduate school on pulsating white dwarfs, and also non-radial pulsators. Very few of those were observed by Kepler, so that's why they're not in here. But they're very small amplitude, and they have actually many different pulsations. You can just see, they kind of move up and down here, and you can see there's sort of this beating pattern that runs throughout them. They have small amplitudes, which made them very hard to observe from the ground. And now, because they have they have 4 years of data, they can actually see how the pulsations change, which was hard to do from the ground. Then we also measured explosive things like novae, these cataclysmic variables, where like every 10 days this material from this big puffy old star lands onto this tiny little white dwarf star, and then the material actually, the hydrogen fuses, so it explodes, and you get these big outbursts. So this is a 400% change in flux you're seeing here. So that's a cataclysmic variable, and we measured several of these. It goes from something that's like 18th, 20th magnitude, for those of you who understand the magnitude scale, up to something that's maybe like 10th magnitude. So it's a huge change in brightness. Suddenly the star's there, and you can measure it. It also did boring things like spots. Here's a sunspot. And as spots just move across the surface of the star, spots change, so they don't do it consistently. So you'll see things get bright and dim. This is the star, the spot moves on across the field, and so it gets dim, and then it gets bright because the spot moved off. And then you can see the amplitude gets smaller at times, like in here, and that's because the spots have changed and have changed size and things like this. And Kepler also observed planets, boring old planets, and they move across and they get these little dips. This is the only Kepler talk where you're going to hear that phrase. So enjoy it while you can. So you get these boring, nothing happens on planet things. And this is what you want for when you're trying to find planets. You want nothing to happen, and then you want these little dips. When things happen like this, it's impossible to find planets. Trust me, I've tried. So then we found tons of eclipsing binaries. These are just sort of left over in our planet search, because you can see they're actually not a whole lot different than what a planet looks like. Occasionally you just get these dips, especially for what we call a detached binary, two separate stars as they pass in front of each other. You'll suddenly get a primary eclipse where the hot one gets covered up, and then a secondary eclipse where the cool one gets covered up. That's here, it's gone behind. And so occasionally you have two stars that are touching, and then you get an eclipsing binary that looks more like this. You see there's variations in between because it's just, and these are far more complicated to model. So that's the eclipsing binary. These are the binary systems everybody was ready to study when Kepler launched, and there was a whole team of people ready to study eclipsing binary stars. There were teams of people ready to study spots. There were teams ready to do cataclysmic variables, all of this stuff. And then we saw this. That's what we saw. And we said, okay, I wasn't quite working on the team yet. So Bill Welsh saw this, and a few other people on the Kepler team, I'll be honest. And what's unusual about this is you're like, okay, well, I see lots of little ups and downs down here. So that's like pulsations, maybe. Those, they're not too bad. Now, if it looked like this, I'm okay with it, right? That's just a transit, right? And you're like, hey, it gets dimmer, great. But that's not what it looked like. So we had to give up on that's not a transit. Some people thought maybe there was black holes involved, et cetera. So what you do when you get something you don't understand, you tend to take spectra of it. That's what you do in astronomy, because then you can learn more. So you split up the light into that spectrum, and immediately what they saw was this. Now, first of all, they could say, okay, well, these are A-type stars. Just trust me that when you see things like this, it's an A-type star. A-type star means that it's hot. It's like 8,000 Kelvin. For reference, the sun is like 5,700 Kelvin. Okay, so much hotter. It's much hotter than the sun. But if you look really carefully, every time one of these, those dark lines I was talking about, that's what these represent, these dark lines, these spectrum. So this is where the brightness dims at this particular color. It's split into two. And you go, spectroscopic binary, right? It splits, those lines have split into two. And if you plot that up over here, this is a radial velocity curve. So radial velocities is what you measured, those velocities moving towards and away from you. And so it moves away from you really fast, and then it moves towards you all of a sudden, and then it takes a slow time to move really fast and then really slow. So the velocities are changing drastically, and this is a signature of an eccentric binary. So what we actually have is two A stars in a very eccentric binary. And those brightness variations happen right at the same time that the highest differences in velocities happen. So I've modeled this up for you because that was a lot to take in, and I know. So what you see here is to scale this binary system. If you imagine these are your two stars, and they're going around a center of mass, their common center of mass. I've already shown you this in others with those two circles going around each other. And this is the distances are to scale, and the sizes of the stars are to scale for those blue dots. So this is an A star, 8,000 Kelvin star. And its orbit has a semi-major axis of about 0.4 AU, where 1 AU is the distance from the sun and the Earth. And so for reference, this is Mercury's orbit. So think of Mercury around the sun. So if this was the sun at the middle, this is Mercury's orbit. In fact, that circle is the size the sun would be on the scale. So think about this for a second. We have Mercury, that really hot, desolate planet that's so close to the sun, it's hard for us to even go and visit it and measure anything because it's so hot, because it's so near to the sun. Now these two stars are getting that close to each other in comparison. That's what's happening in this system. They're getting within about 5 solar radii of each other, 5 to 10 solar radii of each other. They're getting that close. And at that time that happens, what you're seeing is this brightness. That's exactly when this thing gets super bright. So why do we see it that way? That's the question, and that comes down to tides. It comes down to understanding tides. Tides is a differential force. Yes, I have a question.
So they're similar mass?
They are. Exactly. Sorry. Yeah, they're about the same temperature, and so as a result, they're almost identical in mass and almost identical in size, which makes it very handy. Yeah, another question. I'll take a few questions. It's a good place.
Those two in this thing here. Now, are we considering that we're looking at this flat on or somewhat edge on?
So that's a very good question. I glossed over that. The truth is with this system, you are looking at it almost entirely as you're seeing it here. So that the plane of the system is perpendicular to your line of sight. However, there has to be a little bit of inclination, otherwise you wouldn't see those doubling of the spectral lines, right? Because you need a velocity moving towards and away from you to see that. And so actually the whole thing, I think, is inclined at about 5 degrees. Okay, so, but that's enough to see those, those velocities. So this is actually a very good depiction of what you would see on the sky if you could just get a telescope powerful enough to actually resolve the location of your stars. Okay. So tides. So tides are a differential force. This is the thing that causes the water to come in every day, the water on the earth to rise and fall. And we usually think about it in terms of the moon. So the moon goes around the earth and the moon pulls on the earth, but it's closer to one side of the earth than the other side of the earth. And so it tugs on one side more strongly than it tugs on the other side. And as a result, the earth kind of feels like it's being pulled apart ever so slightly. And that causes it to be, to first order, sort of this oblong shape. And that's what's happening with these stars as well. So it was hard for me to think of a unit to describe to you how strong this tidal force was, so I'm going to do it in units of the strength that the moon pulls on the Earth, the differential force that tidal force, because it's the only thing I can relate it to. I could give it to you in actual units, but it would mean nothing to you because it meant nothing to me. Then again, you might be better off than me. Maybe you'd get it. But so for this system, the tidal force out here, it's only twice as big between the two stars. So if initially one star is way over here and the other one's off the screen over here, and then they come through periastron. This is no longer to scale, but I needed a way of blowing up what's happening with the tidal forces. And you can see as they get closer and closer to each other as they go around the orbit, suddenly at the middle, they're 4,000 times, that the tidal force is 4,000 times stronger than the tidal force between the Earth and the sun. Sorry, the Earth and the moon, sorry. That's what's happening here. And so as a result, the thing becomes just a little bit oblate. Now, when you get something that it's gone just a little bit oblate, go a little bit ellipsoidal in shape, it actually has a slightly larger surface area. And when you have more surface area emitting light towards us, it gets brighter. Increase in surface area, increase in brightness. And so that's in part what's happening to cause that brightening that we see in the KOI 54 system. I don't know if I told you the name of the system. We call it KOI 54 that I showed you. And so when it comes through here, it gets bright simply because of the tides. The other thing that's happening actually is the irradiation. They're getting so close to each other, they're heating each other up. And from that, you get this extra brightness. Increase in temperature, also an increase of brightness. So here is a little movie of it, because some people prefer to see movies. The exact scalar accuracy of this, if I can get it to run. Da, da, da. No, I can't get it to run today. It ran yesterday. Try again. It's supposed to just go. There it goes. It just goes. So you can just see, that's what happens, right? See, everybody likes the movie. It's much better as a movie. Can I play it again? That might be beyond my technical abilities. So one thing to keep in mind here is the perspective changes. We actually zoom in on the stars so you can actually see that sudden change in the shape of the stars. So you can tell it's not exactly, it turns into ellipse, it's more like it turns into a teardrop shape if you wanted to talk about it more specifically, independent of the star. So that's KY 54. Then what happened was, so this is KY 54 at the top. I just explained that to you, why we get those brightenings because of the tidal forces and suddenly seeing this ellipsoidal shape. Then we started seeing all of these guys. And you go, well, Susan, those don't look anything like KY 54. Why are these on the same slide? Right? I mean, I showed you all those other variable stars. Why are they any different than these? And except for the fact that they kind of just go along and then they suddenly jump up, right, change in brightness. So how do I make these all look the same? How do I make this all part of that same physical system? And that comes down to understanding your change in perspective. So if you think about it, as that great question asked, our perspective for KY 54 is it was basically plane on. Now think about, so that's what you're seeing down here. This is a grid of what the brightness changes would be versus time for if you were looking at it for different inclinations, going from low inclination up to high inclination. And so if this is KY 54 here, where it just gets bright, you kind of see how that looks a little bit like the KY 54. This is a model now. But if you just increase the inclination, so going from plane on to more tilted, more tilted, more tilted, what happens is that you get it to go up and then down. And the reason that happens is if we go back to here, now I'm going to separate slow, of course, is that instead, what's happening is instead of standing such that you're looking down on the plane, you're actually standing down here at the bottom of the screen, down here, and you're looking up at it. And if you imagine as it comes through, what you're actually seeing is you're seeing the shortened side, the tip view that's shown down here. So you see the tip, which is a smaller surface area, right? And so as a result, it gets smaller, you get a decrease in brightness. And then it comes through and you'll see a big wide side here. And it suddenly gets brighter, and then it'll come back through and see the back side of the tip, right? And so you go dim, bright, dim. Yeah? So that's what you're seeing here. It goes dim, bright, dim. And then you also get these other shapes by just changing whether or not you're looking down from the bottom of the screen over to the side of the screen. So you can actually, that's called the angle of periastron. And so it's whether or not you're seeing it from over here, where you can imagine you can see bright, and then I would see bright, and then dim, and then bright. It would go up, down, up instead. Because if you were standing over here, that's what you would see. Now, of course, the largest tidal forces happen right at periastron, right when they get closest to each other. So that's when the largest change in flux will happen. But if you're standing over here, you'll see that change in flux be dim because you're seeing the very tip of it instead. Okay. So from that, we're actually able to explain all of these shapes that we see. And this is just a simple, the green model here is just a simple mathematical model to show what sort of brightness changes you expect to see for these different types of heartbeat stars that we see. And so you get all of these shapes explained using this simple model that was actually published back in 1995 by Pawan Kumar. And it does a pretty good job. And then if you throw in the irradiation effect that I talked about as well, you do an even better job. And then what's left over before some of you ask is all these little ups and downs as well, the pulsations, which I'll talk about later. While we see these things, oh yeah, go ahead.
What's the speed change when they reflect?
You mean what's this velocities that we measure right as it goes through periastron? It depends on the masses of the stars, so it does vary quite a bit. And honestly, well, actually, this is a perfect slide for that, except for I don't think, yeah, here they are. So for this star, for instance, which, let's do this one. You can see this is the radial velocity side. So from what we can observe, so it depends on the inclination, but if you assumed it actually was on edge on, then you're getting speed changes about 50 kilometers per second. Some of them may be as high as 100 kilometers per second. And that's what these measurements are. This is the radial velocity measurements I was talking about before, taking those spectral lines and actually measuring the radial velocities. And you can see that they all have this, like, crazy up-downs that you see that is indicative of an eccentric binary. And so from the radial velocities, they actually truly measure the eccentricities of these systems. It turns out it's very hard to measure just the flux-like curves that we see here, the brightness variations, so that it's easier to get the eccentricity if you go out and get the spectra and do the radial velocities. So from the Kepler data, we have found about 150 heartbeat stars. And this is where they're found across that field of view, and they've been colored by how bright they are. So the red ones are the brightest, and the blue ones are the dimmest. And so it looks like, you know, there's more down here than up here, but that's sort of expected because there's more stars down here than there were up here that were observed by Kepler. So that's why you see it that way. If you want to know just a little bit more about what they're like, the periods tend to be mostly around 10 to 20 days is most of them, but we do have a few that are out here like 150-day periods. You also find that they tend to be around hotter stars, like 6,000 to 7,000 Kelvin stars, so things that are hotter than the sun. That means you'll be more likely to see a heartbeat around them. This seems to be because the amplitudes of the heartbeats actually have a trend with their temperature, and that's because the hotter stars tend to be a bit puffier, and so it doesn't take as much of that tidal force to pull them more out of shape, and to, as a result, see a higher amplitude heartbeat. And then from those radial velocity measurements I showed you that were kindly collected by other people on this team, you can plot then those eccentricities versus period. And the gray are just normal eclipsing binary stars, normal. Some of them are not very normal at all. They're super high eccentricities and very fun to study in their own right. The red ones are the heartbeat stars that we've measured the eccentricities for. And you can see that they kind of trace out the upper envelope of where you actually can find highly eccentric binary stars. For instance, what you notice immediately is there aren't any short period highly eccentric binary stars. It turns out when you get to that short period, the tides immediately wipe out the ability to be in a high eccentric system. It's very difficult to maintain your eccentricities if you're in a really short orbit. And that leads nicely into just talking about some of the fun effects of what you can actually see because of these heartbeat stars. If I've lost you now's a good time for questions. Because it's only going to get worse. Yeah.
curves that you models, they look an awful lot like mass-free system. You put like two masses linked together with a spring potential.
Oh, that's a very good observation. You mean like KY54, how it kind of oscillates back and forth. And that is a great analogy to hold in your mind, that these light curves look a bit like a spring system if you plot up the distance versus time of a mass on a spring, is what you're referring to, yes? Yeah, and they go up and down. And it's because it's a harmonic oscillator. And it's a very good analogy to think about when, especially as I keep going, because you'll see another harmonic oscillator, the pendulum, coming up really soon. So yes, that's a good analogy to hold in mind. But they are different because they're a 3D thing that's oscillating instead of just a one-dimensional object. Though I agree, the one-dimensional one is way easier to think about. Any other questions? Yes?
Yeah, just like it is, but because they orbit so close to each other, are they exchanging mass with each other?
We don't believe that they are. They're actually massive enough and not getting close enough to each other that they aren't. There's something called the Roche lobe, and that's the distance you have to get to be able to pull mass from one to the other. And these stars are dense enough that they'd have to get much closer together to actually pull mass off of each other.
Is this diagram supposed to be showing a cross-section of the stars if you took a plane and cut through the centers of the star?
Yes, except for that it's supposed to give you the impression of seeing a three-dimensional object, that it's actually, there's sort of like a temperature grading running across the surface of the stars, to give you an idea. This is not a perfectly modeled astrophysical system that you're seeing here. It was sort of more of a movie thrown together to show you essentially what's happening. But yes, you can think of it as if you cut through the stars, what shape they would take on.
Or is this dark area the pole of the stars?
So look, yeah, you're like looking down at the pole of the star here, and so instead of it being a circle, you're seeing it more like a teardrop shape. Does that make sense? And so I don't have a good picture of that, but you can imagine a big ball and it goes into like a little teardrop on one side. Yes?
Well, I guess eventually these close binaries will eventually touch because you're losing orbital energy due to this gravitational compression and contraction. So eventually the orbital period will start to increase as they get closer and closer. And so there's a finite time that these objects can orbit each other before they eventually coalesce.
So yeah, you're asking about the decay of the orbits of these objects, and it does depend on if they're the only thing going on in the system or if there's other bodies that are also in the system. As they lose angular momentum and energy and it's exchanged between the two stars, what we expect to happen is that the system will circularize and you'll no longer have a highly eccentric body. And that's a great lead into the next stuff I was going to talk about, so I really thank you. It's like I planted you there to ask me all the great questions. Go ahead.
How much of a range of differentials of the masses are there of different pairs, and to what extent does that mitigate or increase the effects?
That is a great question, and one of the ones we'd love to be able to answer. We actually need to get more radio velocities to know what the distribution of the different masses are. We see ones like KY54 where both stars are very similar in mass and they're both really massive. They're both about 2 times the mass of the sun. But we also see ones where we see no evidence of what that other body is other than the effects it has on the spectral lines of the first body. Like we can't see the lines from the other ones at all. It's too dim, which means that it's probably something that's like half the mass of the sun or something like that. So we see all types. We haven't measured enough of them to tell you what the distributions are. But it is true, the larger the mass that you have and the closer they get to each other, the more tidal forces you have, the more radiation you have, and the more likely that you'll see something look like a heartbeat star in its light curve in the end.
What are the 3 layers of color? Like the middle is dark, and then there's red and yellow on the outside.
Oh, you mean on this thing? You know, I think the intent of this was that you tend to have a hotter star as you look down on it. It is hotter in the middle and it gets cooler around the outside. So this would be the hottest part and this would be kind of cooler. But the effect that they're describing is something called limb darkening, and I'd really rather not go into it. Yeah, so don't try to read too much into this diagram. I know it makes a great, pretty picture, but mostly the thing to focus on is the shape change that happens and how that you suddenly have more surface area on your star. One more question in the back there.
The extension of the star is friction of it, stabilizes it in a way. Its internal energy, its internal power kind of blow across.
It's not going to destabilize it as much as it's going to cause the energy to be lost in the system in the form of heat. So you'll actually lose energy in the system because that tidal interaction, as it pulls on it and it comes back, you end up with friction basically going on. And so that gets lost. I don't expect these tidal forces to then spiral into something that would cause you to lose one of the stars, for instance, and throw it off. It's not that, I guess, aggressive of a thing that's going on. All right, you guys are already asking the great questions about some of the things that we're going to talk about here. So I'll move on, and you can ask me more at the end for sure. So what happens? So we already talked a little bit about with the questions about how the orbits are going to decay in these things, and that comes down to because you have these two stars going around each other and creating these tidal bulges, but the tidal bulge doesn't happen instantaneously, so it's always kind of delayed behind, and so as a result, just like in the Earth-Moon system, every time I talk about tides, if you go to try to find images on Google or Wikipedia, et cetera, you always find Earth-Moon stuff. And I need to make graphics with stars, but if you can imagine this was one star, and this was the other star, but the way it pulls on it creates that tide, and then they pull on each other, but it creates a torque. You can think of a lever arm pulling a force down, and so it pulls on the rotation of that star and asks it to slow down. Hey, come join me in the period that I'm going. So it slowly tries to take that, it slowly changes the rotation period of the star. And this happened in the Earth-Moon system, that the rotation of the moon is the same as the orbital period of the moon around the Earth. This is why there's the dark side of the moon, which isn't really dark all the time, but certainly we can't see it. That's why you always see one side of the moon. The rotation period has lined up with its orbital period. So we expect this to also happen in our stars, this synchronization of the rotation. The thing is, ours don't have a consistent angular frequency that is moving through. So as a member, we talked about this orbit again. You notice the star goes slow, 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 fast, and then it slows down again. Well, if this was circular, it just moves the same speed the whole time, like you see in the Mercury orbit here. It goes around at the same rate the whole time, and then that would be fine. The rotation could match that period. But it can't match it here. Here it would have to go spin super fast, and then when it got out to the distance, when it's at apastron, it's the farthest away, it would have to go really slowly. So instead, what we expect it to do is have that rotation period match sort of the average of those. And that would cause no net torque over the whole system. So it pulls and pushes until hopefully you get this pseudo-synchronization of the rotation period. And so we say, hey, I wonder if that's happening. We predicted it should happen, let's go out and test it. And so I put an intern on this last summer, Mara Zimmerman. She did a great job for me at measuring the rotation periods and the centricities of a bunch of heartbeat systems. So the way we got the rotation is back to those spots. Those things that are annoying us with the planets. Some of our heartbeat stars, there's a heartbeat. In between, you see all these other pulsations, but they're not very regular, so they're not pulsations, they're spots. And so they kind of come and go. And so she went through and measured how often she saw them go up and down and up and down. She did it with something called a Fourier transform, and I probably shouldn't have even put this slide in here, but for those of you who know what a Fourier transform is, these little peaks here, which this is frequency versus amplitude, These peaks here say, those are my rotation from the spots. And as a result, she could measure the rotation periods for, I think she's about 17, 15 or so of my heartbeat stars, of our heartbeat stars. And then she also predicted what the pseudo-synchronization period be based on the orbital period and on the eccentricity, which is based on an equation that was published in 1981 by Hutt. And you can see that many of our heartbeat stars fall along this line, which is the line of pseudo-synchronization. But what's interesting is some of them really do not. And so every time you ask a question in science, suddenly you end up with another mystery. You go, because the truth is these stars should reach pseudo-synchronization really quickly. The lifetime of these stars is something like 100 million years, but they should pseudo-synchronize in about 10,000 years. So either they only recently became highly eccentric, which is its own little mystery, or there's something else in the system that is keeping it from reaching this synchronization between the rotation and the orbital period. And so our best guess is maybe there's a third body in some of these systems that we could go out and look for. And so that's where this is left at this point. The other thing that influences the evolution of these systems is actually all those pulsations you were seeing in the light curves I showed you earlier. And this comes back to our harmonic oscillator that we mentioned and the pendulum. So I have a 4-year-old, so I think of swings. And so if you have something that likes to oscillate at a particular period, such as a buoy in a swing, the oscillation period is dependent on just the length of the string, the length of the chain on the swing. But for a star, it depends, like what it wants to pulsate at has more to do with like the mass of the star, or the temperature of the star, or the size of the star. But it is possible to make a star ring if you line up that orbital period with one of the frequencies that that star wants to ring at in the first place. If you achieve this thing called resonance, you'll get the star to ring. So if you had a buoy in a swing and you wanted to achieve this resonance, what you would do is you'd push the buoy every time he came up to the top. So at the period he wants to swing at. You pushed it every time he came to the top, you'd achieve resonance, and voila, he would be swinging. If you push it every other time, that even works, right? You know, every time he came up, you skip one, you'd still achieve a bit of a resonance and the buoy would swing. If you tried pushing him instead at just random things that did not match at all, the buoy does not swing, there is no resonance. All right? So in these cases, if the buoy was our star, you would not see pulsations, okay? I know, this poor kid, he needs a better daddy. The one who stops performing physics experiments on his swing set. So stars have natural resonant periods, and if the orbital period, because what's happening is the star, that other star's coming in, and it's almost like it's hitting it like a gong and says, ring at this period every time it comes through. And if they line up perfectly, you'll get things that actually do ring. You'll get, if you look at the light curve, what's left over are all these pulsations that run through. For KY54, you can see it throughout here. There's the 91st and the 92nd harmonic. Harmonic means 91 or 92 times the period, the orbital period. Actually, divided by the orbital period, sorry. So it's much faster, you get in between. And so that's the stars ringing at that period, just showing it's oscillating at that frequency. Yeah?
Is the ringing sort of a distortion of the shape to sort of one shape to spherical, or?
It's much more subtle than those tidal effects I was talking about, but there is a slight deformation in shape. What mostly happens is the material kind of moves along the surface of the star. In fact, these are gravity modes, so they're more akin to something like ocean waves. If you want to, it's the closest thing I can come to what they're like. But the material moves along the surface of the star, making one part of it hot and another part of it cold. Yeah. It's a reasonable approximation. And so this is where to really hit the point home. Some people light curves, they don't work for them. But if you translate these light curves into sound waves, so if you compress the frequencies into sound waves, you can actually listen to what happens when these dancing stars decide to make a little bit of music. And see if this works. Have my volume up. Gonna work for us today? Got it to work either. It's not giving it to me. Oh, I led you into this, and now you just don't get it. Oh, there it is. It's just too dim. Is there somebody who has volume? Make it any higher? Yeah, it's up all the way. Because I can just hear it. You hear that buzzing sound? That's what we're going for, but you can't. I was hoping it was much louder before. Oh, I'm so sorry, guys. Is there another place I can turn up the volume? I didn't touch the volume, though. Maybe if... Give me a second. I'm going to view this by slideshow, and maybe the buttons will work better. Let's try again. No, I woke you all up, didn't I? All right. So this is the music of the spheres, the music of the stars. But you hear there's two pitches in there, right? You hear that ooh, up at the top. And then there's also that buzzing sound that runs through there. That buzzing is more the heartbeat. And also there's this little eclipse that happens here, which I think adds to that extra buzziness of it. And then there's that high-pitched thing at the top. So that's what you can think about when I'm talking about these pulsations. Because that buzzing thing's happening down there, it's causing this other thing to ring at a higher pitch. Since we got it working there. So this one, the actual pitch you're listening to depends on how I translated the frequencies down into our audible range. Okay, so keep that in mind. There was a bit of, magic, jiggery-pokery involved in making these. But again, this one's because the pulsations are more similar to the heartbeat period. There's not that separation. You mostly just hear kind of one frequency. And then this one's KY54. And this one's really cool because it sounds like a heartbeat. It has that beat and it has those two beating frequencies up there. They're very similar frequencies to each other, and they kind of go woo, 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 woo. And that's why you actually see them beat. You see how the envelope of the outer envelope of those pulsations go up and down. All right. So now that I've woken you all up. What's cool about these tidally induced pulsations is that we actually believe that at times they might just be happenstance. Maybe as those orbital periods are changing because of the tides, it drifts through a period at which you end up reaching this resonance frequency. So it's just chance. But it's also possible when that happens, it locks into this resonance mode such that those because it's pulsating, it actually changes the evolution of the binary system altogether. It changes the rotation of the stars, and it changes that orbital eccentricities and the periods. And so they lock in steps, so you maintain the resonance for longer than you would have otherwise. And so as a result, the binary system's evolution changes because it reaches these pulsation modes. And that's partly why these tidally induced pulsations are so cool. This is something called resonance locking. If you want to know more about that, I highly recommend you get Jim Fuller up here to talk about it. But here's one system where you can see the pulsations are much larger than the heartbeat. See, the pulsations are huge, and then there's just this is just a zoom in of that central region there. Sorry, there's just that little central region right here, you can see it just goes like that. That's the heartbeat right there. And then on top of it are these pulsations, and they're larger than that tidal distortion part is. So it came in, and this is actually a huge eccentricity. This is a period of 87 days, and it has an eccentricity of almost 0.9. Remember, 1 being a straight line, so 0.9 is highly eccentric. And so because it's so eccentric and has this strong tide that pulls it, so it's caused this thing to ring. And the thing is, this amplitude is so large that we believe it's really hard to produce this by chance. And so it's just the likelihood of observing this at this time point would have been hard. And so that's why we believe resonance locking is going on, and these pulsations are actually influencing how these stars evolve, how these binary systems evolve. So then the last effect that we've seen with these stars, which is interesting, is something called apsidal motion. And this is the precession of the orientation of the orbit around each other. And this is just this, I've simplified it down to just as if all the mass is in the center and this is like a planet. And you actually see this in Mercury's orbits, like how the eccentricities line, it rotates around. And this is called apsidal motion. So originally the orbit is like this, and then you'll see it progress around, and it'll be aligned this way instead. So, and the question is what causes that? And it comes down to the fact that anytime you have like an asymmetry in the mass, for instance, that happens when you get these tides, these tidal deformations, you can cause this extra tugging, which causes the orbits to move around. The other thing that can happen is if you put a third body in the system, or a fourth body or whatever, that also can tug on the system and cause that line of the angle of periastron to move. And this is what's called apsidal motion. And a paper just last week came out by Kelly Hamilton showing that she's found one star that does this. And what's cool with heartbeat stars, remember I told you it all has to do with perspective, is how you see that heartbeat star. So if you saw it initially with an angle of periastron of 0 degrees, you would see it just get bright. But then you'd note it, if it was actually moving around, sometime later you'd see it go bright then dim, and then later you'd see it form a W shape. And it could go through all these different ranges of brightness variations. Now, unfortunately, this happens really slowly, even in the most extreme cases. So this is what she was able to actually observe. This is actually 3 different times in that 4-year-long Kepler data set. And you can just see, like, if the first year was in red, and then, which goes like that, and then by the end you have it in black. And she, with precise statistical tools, able to measure that the angle of periastron at the beginning of the Kepler mission and at the end, and found that it precessed by about 1 degree per year. So 4 degrees over the whole year, over the whole mission. And so and even that means that it has to be the most extreme case of thing that's causing this precession. It can't just be the tidal deformation, which only causes like 0.007 or so degrees per year. So it's most likely that there's a third body in the system that's causing this apsidal motion. So I know that was a lot, and so I hope you got something out of it. Essentially, there's all these dynamic tidal forces in these binary systems, and we were able to observe them with the Kepler Space Telescope because it has this amazing photometric precision. We can measure the brightnesses so precisely, and we were able to measure them consistently over a 4-year period. And as a result, we found this sort of a new way to actually look at binary stars. We're not just looking for eclipses anymore. Now we can actually look for heartbeat stars. And so I'm hoping that you appreciate my title by now, actually, when binary stars get funky. And if you don't, I'm going to prove it to you. If you go online and you look up the word funky, Free Dictionary says it's unconventional or eccentric. No doubt, eccentric. Check. Funky. Urban Dictionary says different but cool and nice, and I certainly think they're quite cool, and they are quite different. Very few of them. There's only about 150 that we know about, and even with the K2 mission, the Kepler extended mission, we've only found a few more. But it's partly that people just haven't looked. They're hard systems to find. And Oxford says, having or using a strong dance rhythm. And I woke you all up with their dance rhythm tonight, so they definitely indeed do a little dance and create their own little music. The only one I disagree with is they're not offensively malodorous. At least I've never smelled a star, but so thank you very much for having me. I hope you learned something, and thank you. All right, I already see questions. Yes, go ahead.
Will the Gaia spacecraft astrometry help us understand these systems better?
The Gaia spacecraft will most likely give us distances to these stars, which will feed into our basic understanding of what they are and how intrinsically bright they are. I haven't worked out all that Gaia is going to contribute yet, so I can't give you a more precise answer than that. But yes, Gaia is going to give us amazing things, and if it doesn't feed into this science, it certainly is going to feed into a lot of similar science, which will help this out. Yes.
These are with evolves from the same sort of protoplanetary.
Yeah, we expect that these stars would have had to evolve together. We don't think it's some sort of capture that happened to get there. It is a question as to why, in the first place, would these be in such a highly eccentric system, and one we would like to answer. I don't even have great theories for you on that, other than invoking things like magnetic fields and third bodies, which you should take very suspiciously. Yes?
Maybe I may have not heard correctly, but I thought it said that 30% of star systems are binary.
It's a very loose number, and it depends on quite how you phrase the question. And so mostly I just want to say that binary systems are not uncommon. There are quite a few that are in multi-star systems. Again, it depends on how you phrase the question. You know, what do you mean by binary? You know, what type of star are you talking about? Where are you looking? There's all sorts of questions, which is why it was hard for me to come up with a good, strong number to quote for you today, but it was one I wanted to find. But I'm going to go and look harder now.
Follow up, this is maybe way off topic, but I read in the magazine that black holes actually can be binary. They can actually orbit one another, and their orbit is very different than the other types. Their orbiting pattern it looks a little bit like waves. Like, for example, black holes, I think, will orbit around each other twice before they venture out in the elliptical path.
Oh. I don't know anything about eccentric binaries with black holes. Certainly black holes do, or are seen in binary systems. That is how they found the first gravitational waves, which you probably heard about in the last year. What is true is they're point masses, but the way that they're interacting with each other has to do with a lot of general relativity and understanding those systems they come through. So I wouldn't want to venture too much into what happens when they get eccentric, but I would love for you to give me a reference on that so I could go look it up. Yes?
I wondered about the orbital dynamics of, say, you have a binary of two stars of equal mass orbiting in a circular orbit. So would the two stars always be opposite of the central gravitational, the center of gravity would be in the middle, and they would always orbit around, like opposite each other?
Yes. So if you have two stars going around each other, do they always sit opposite each other as they go around that central center of mass? It really doesn't matter if they're of equal mass or not. So this is an example of what I showed you here. The red point is the center of mass. They both orbit around that center of mass. And so then they'll always be on opposite sides of their orbit as they do so. Yes?
Do they have to be in the same plane? Suppose they were initially started, the momentum vectors.
I think you would find that that's actually not physically possible. You have a dynamicist over here who could probably answer that more precisely than me. But because the angular momentum vectors have to line up. It is true that you can get planets that are not in the same plane as the rotation of like the star, but for binary systems, like it's really just a pure binary system, in order to solve Kepler's equation and all this, you actually need the forces the way they tug on each other is along the same plane, and so then they get pulled in. So they have to be sort of in plane. You can't have one going like this around the center of mass and the other around this. That center of mass, the reason it's called that, is actually the place that's between the two stars. That's all that really means. So they both have to, that place has to always be between the two stars. So if one was going like this and the other was like this, when it was out here, the center of mass would be over here, and so you'd have a moving center of mass. And so I can't make that work with only two stars. Does that follow that sort of? Are there other?
Sorry, the crowd's noisy in the back. They're all excited about the funky stars. I want to thank you so very much for speaking to us tonight. We enjoyed it and learned so very many things.
Good.
Thank you very much.
All right, thank you.